In this video, I will explain the theory of Bronsted-Lowry acid and bases. So the first thing to point out is there are several types of acid-base definitions, and Bronsted-Lowry's definition is just one of them. It is one of the most applicable because it's very general and applies to many different types of acid-base chemistry. So that's why we'll be talking about it today, and it's why it's commonly used amongst organic chemistry definitions of acid and bases. So, first thing to point out is that Bronsted-Lowry acid and bases are defined by the movement of protons, which is hydrogen atoms, and they function with this idea of pairs, where there is an acid and then a conjugate base pair, or a base and conjugate acid pair. I'll work through several examples to explain how you identify the acid and base pairs and what this conjugate idea means, but this is the entire idea of the Bronsted-Lowry definition, and it's useful to keep that in mind as we're doing all these problems, that it's the movement of the protons that we are looking at here under this definition. So moving along with that, acids and bases in this definition are defined by the movement of the protons, like I just mentioned. So acids are proton donors. They give up a proton. For example, this acetic acid molecule could donate this proton, this hydrogen atom, to a Bronsted-Lowry base, to another molecule. The molecule that receives the proton, is the base, and they're therefore defined as a proton acceptor. They are accepting the proton donated from the acid. And that is the basic idea of Bronsted-Lowry acid bases, is that you're looking for the movement of a proton from one molecule to another. Now, the good thing about, or the useful thing about Bronsted-Lowry acid bases is that it can be, the strength of the acid can be defined by the pKa. The pKa is simply a measure of an acid's strength. So the lower the pKa, the stronger the acid, and it's derived from the equilibrium constant. So as a quick review from general chemistry, pKa is the negative log of the Ka. Ka is the equilibrium constant for a dissociation reaction of an acid. So what I mean by that is it's this reaction. So you have some generic acid HA that's in water. This is just a solvent. It's heavily diluted, so we just call that liquid. And HA dissociates into H plus and A minus. This is H3O plus because it is a proton, a hydrogen, plus H2O. So the Ka is expressed, the equilibrium constant is expressed as products over the reactants, where the product is concentration of H3O plus times concentration of A minus divided by the concentration of HA. We ignore H2O because it's just our solvent here in this case. This is heavily diluted, so we don't consider this as contributing to the equilibrium constant because this is going to be much higher concentration than everything else in the system. So to get an accurate understanding and accurate measurement of the dissociation, which is what we're interested in this acid chemistry, is you ignore the H2O, and then you get this expression. So using this expression, we can explain why the lower the pKa means stronger the acid, because the lower the pKa, the larger the Ka, which means that the larger the concentration of H3O plus and A minus is. And that means that HA is disassociating into H3O plus and A minus more often than it is going the other direction. So if we look back at this equilibrium, HA is becoming H3O plus and A minus more than A minus and H3O plus are becoming HA, which what that means is HA is donating its proton to the base, the Bronsted-Lowry base, more often than this is going the other direction, which tells us that HA is a better Bronsted-Lowry acid, which therefore explains why we have lower the pKa is stronger the acid, because it suggests a larger concentration of the products, which is what we want here if this is going to act as an acid. So there are several factors that influence the strength of any particular acid and therefore influences the pKa of that acid. So the first thing is electronegativity. So the electronegativity of the atom bound to the proton that is acidic, the more electronegative it is, the higher the acid strength is for that. So this is what I mean here by this this expression here, we have CH4 that is less acidic than the NH3, which is less acidic than H2O, which is less acidic than HF. So what we're comparing in terms of electronegativity is the fluorine compared to the oxygen, compared to the nitrogen, compared to the carbon. So we know fluorine is the most electronegative of these options here, making this the strongest acid. So this HF would have the lowest pKa, and therefore it is the strongest acid among this list. So one thing to point out while I'm looking at this is we are always talking about the acid strength of a proton of a hydrogen atom, a proton in the molecule. So here we're comparing effectively how well this hydrogen can be donated to a base, or how well one of these hydrogens in water can be donated to a base, or how well this NH3, any of these hydrogens, etc. So the idea now is the electronegativity is simply affecting the likelihood that this hydrogen will be donated, which then again is how likely this is going to function as an acid. Okay, so the next thing to talk about is the hybridization. So the more S character, so the higher the S character, the more likely, the more acidic, the more likely that proton will be donated. So more S character, more acidic. So what I mean by that, if we recall, these are all sp3 hybridized in this case because there are 4 bonds to the carbon, so it has a tetrahedral molecular shape and geometry, so hybridization is sp3. So this guy is not very acidic because it only has 1/4 S character here. If we move along now, these carbons are sp2 because of the presence of the double bond, so it now has 1/3 character of S, of the S orbital, making these hydrogens slightly more acidic than these ones. And increasing further, this is sp now, that is 50% S character for these hydrogens, so they are the most acidic of this chain. So this is most relevant for just these alkanes, alkenes, alkynes type of structure, but it's still relevant because this alkyne hydrogen is quite acidic, so we can take advantage of that in synthesis and other problems that we'll do in the future. So just keep this in mind. Okay, next is the inductive effect. So the inductive effect is simply if there are electronegative atoms that are close to the hydrogen that we're looking at in terms of its acid strength, then it will increase in acid strength. So here we just have ethanol. So we're looking at this hydrogen for its acid strength, its ability to be donated to a base. This isn't particularly acidic, but if we add a chlorine to the carbon that's bound to the OH, that increases the acid strength of that hydrogen here. And we can increase it further by replacing the CH3 group with another chlorine, and now these chlorines influence the hydrogen acidity here. So the more electronegative atoms you have close to the hydrogen that is being donated, the more acidic that hydrogen is, or the lower the pKa that hydrogen will have. Okay, moving along. The next thing to influence the acid strength is size. So size matters more than electronegativity. This is important to say. So this is usually more important than electronegativity, because as we look here in this trend, HF is less acidic than HCl, which is less acidic than HBr and HI. So we know that fluorine is more electronegative than chlorine and bromine and iodine. So like I said, the first factor is electronegativity, so you would suggest based on electronegativity that HF would be the most acidic proton here. However, the size matters more because a base would be able to accept the proton easier because of the size rather than the electronegativity. So HI is in fact the most acidic in this sequence, then HBr, then HCl, then HF. So you need to keep in mind that these are all factors, but there's no hard fast rule to indicate which is always going to be the most acidic. You have to consider them all collectively to identify maybe one acid has more of these characteristics than another, but the big takeaway is that size usually wins over electronegativity. But again, I'm only saying usually because these rules aren't like definite. There's always exceptions, but as a general rule, this will get you correct assessments more often than not. Okay, next we have resonance of the conjugate base. So here I will talk about conjugate base and conjugate acid. So first of all, my list is just that we have methanol. Looking at this hydrogen here, these are not as acidic because they're not bound to an oxygen. When this hydrogen is bound to an oxygen, it makes it more acidic because of the first rule of electronegativity, right? Here we have carbon double bound to an oxygen and an oxygen bound to a hydrogen. So this is extremely acidic. These hydrogens here are not that acidic, again, because electronegativity is the first rule to assess, and we have oxygen compared to a carbon that is much more electronegative, so that hydrogen is more acidic. So this hydrogen is being compared to this hydrogen, and this one is more acidic. So now, if this methanol, if the first molecule were to dissociate, it would make H plus and H3O minus, where this hydrogen has just broken off, creating these two species. Now, the conjugate base is this one. So we have our acid, and its conjugate base is when we've lost the proton that has been donated because it's functioning as an acid. It's been donated somewhere, and this becomes the conjugate base. So our pair, to put this all together, this would be our Bronsted-Lowry acid. This would be our conjugate base. I'm ignoring the proton here because if we had water, then water would be functioning as our base, and then H plus, H3O plus would be the conjugate acid to water, but I'll work through better examples here. I'm just introducing the idea. The conjugate base is losing the proton from the acid, making it a conjugate base. And the point that I want to make here is there's no resonance capability for this molecule, this conjugate base. So this conjugate base is not stabilized by resonance because there's none that's possible there. However, if you look at the acetic acid, which is our other option, if you do the same thing and donate this proton, so this is an acid, here's our donated proton, this is our conjugate base, and now this molecule has resonance. As we've seen before in the previous videos, this negative charge can be delocalized up into the oxygen here, creating this oxygen-carbon double bond here, and moving the negative charge from this oxygen to this oxygen. So therefore, this conjugate base is stabilized by resonance, and that makes the original acid more acidic because this product is more stable than it would be otherwise. So because of that, because of resonance, it is pushing the equilibrium away from this acid and making this acid more reactive or more acidic. So again, this would have a lower pKa than the methanol, than the CH3OH. Okay, for the remainder of the video, we will work through several examples as usual. So here, the first thing that we need to do is identify which is the stronger acid. And again, we're always talking about Bronsted-Lowry and Bronsted-Lowry acids and bases in this video. So here, all we have to do is compare the pKa's since they're given to us. So here, we have 3.3 and 1.3. The lower the pKa, the stronger the acid. So because of that, we know that this H3PO3 is the stronger acid. So H3PO3 is the stronger acid. So those ones aren't particularly difficult because all you have to do is compare the numbers that they give you. The lower the pKa, the stronger the acid. There will be some cases, however, where they don't give you the pKa, and you will have to be able to use the rules that I mentioned, like size and resonance, in order to predict which one would be more acidic. So that type of example is here. So we're not given the pKa's in this case, so we have to just compare. And right away, the only protons we have to look at are the hydrogens off of this carbon, the hydrogens off of this carbon, or the OH hydrogen. So again, the hydrogen that's bound to the oxygen is going to be the most acidic, and that's what we're assessing. So now, the only difference between these two is the presence of this chlorine, right? And because of the inductive effect, the chlorine will suck some of the electron density away from this hydrogen, making this hydrogen more electropositive, more partial positive in our dipole moment here, which what that effectively does is make this hydrogen more acidic. So because of the inductive effect, this molecule is more acidic, is the stronger acid, or it has the lower pKa. Since we weren't given it here, we could predict that this would have a lower pKa than this guy. So, and again, keep in mind, if we were to lose this proton in both cases, they would both have the same resonance that we looked at here, right? They have this exact same resonance structure, even though this molecule here has a chlorine. That doesn't affect the fact that the negative charge could go from here up into the molecule. That is still the same possibility regardless of the case here. So that can't be the difference. The only difference is the presence of this chlorine, which is the reason why B is more acidic than A, and that is the inductive effect. Okay, so now we will get into the hardest type of problems along these lines, which is identify which species is the Bronsted-Lowry acid and base, and then predict which direction the equilibrium lies. So, first of all, here's our first equation, and I'm giving you the pKa for both of these molecules. That may or may not be a part of the question. It will just depend. You can do it with or without it, and we'll do examples of both. But here we have the pKa's. So right away, we're told that the pKa of HF is 3. So we know that this is the stronger acid because it has a lower pKa. And then this must be the weaker acid because it has a higher pKa. So now we know that right away from the pKa values. Now we have to look at the equation and see which is acting as an acid and which is acting as a base. So here we have HF, here we have a negative charge. If we look at the transformation, HF becomes F minus, so it has donated that proton. So that means that HF is functioning as a Bronsted-Lowry, I'll just say Bl, acid, because it's donated its proton to the other thing, to the other molecule. So that means that F minus is the conjugate base of HF, right? And this now, that has accepted the hydrogen, so this is our Bronsted-Lowry base here on the left side of the equation, and this would be the conjugate acid to the Bronsted-Lowry base. So now that we've now done the first part of the question, we've identified which is the acid and which is the base and its conjugate pair. So now the question is to determine which direction the equilibrium lies. Well, we've already established that HF is the stronger acid, which means it's more reactive and it's more likely to form the products. So since this is the stronger acid, that means that the equilibrium will shift to the right. So it's driven to the right. Okay, so because, just as a recap, because this pKa is 3, the pKa of HF is 3, and the pKa of CH3OOH is 5, we know that HF wants to dissociate, so that means that there's more of this product being made than going the other direction. So again, that means the equilibrium is driven to the right, or in other words, you could say it's going in the forward direction. Both of those are acceptable. Okay. Now we'll move right along to our next example. So here, we don't have pKa values at all. We have CH3O minus plus NH3 going into equilibrium with CH3OH and NH2 minus. So what we have to assess is which, again, what is functioning as the acid and what's functioning as the base. So on this side, we have this NH3 is giving a proton to this. Here is the proton that's being transferred. One of these three is going to this molecule. So because of that, this is functioning as the Bronsted-Lowry acid. So this must be our Bronsted-Lowry base because it is accepting the proton from our donor here. So that means then that this is the conjugate acid to our base, and this is our conjugate base to the acid. Okay, now the question is, which one of these are more acidic? Well, the only thing we can compare here is either atom size or the electronegativity. So oxygen is more electronegative than nitrogen. It is also about the same size as nitrogen. So there isn't a significant difference there. But due directly to the electronegativity difference, we can immediately say that this CH3OH is the stronger acid because of the electronegativity. So when we look at these, we have to compare the electronegativity because there's no difference in size, there's no resonance in either of these, there's no hybridization to speak of, nor is there an inductive effect. So by process of elimination, electronegativity is all we have left. So because oxygen is more electronegative than nitrogen, this must be the stronger acid. So again, if this is a stronger acid, it means it's going to drive the equilibrium away from it so it can disassociate into its products. So what that means is this equilibrium lies to the left or in the reverse direction. Okay? So moving along. Here we again are not given the pKa's, so we first need to establish what is functioning as the Bronsted-Lowry acid, what is functioning as the Bronsted-Lowry base. So here we have a proton that is being donated to this molecule. So this is our Bronsted-Lowry acid, and this is our Bronsted-Lowry base. So therefore this is the conjugate base to our Bronsted-Lowry acid, and this is the conjugate acid to our Bronsted-Lowry base. So now the question is we need to assess which of these acids is the stronger acid. Well, the only way to compare that here, if we look at electronegativity, they're both bound to an oxygen, so that there isn't really a difference there. If we consider size, it's the same molecule, or the same atom that it's bound to, so there's nothing there. Hybridization isn't significant here because it's bound directly to the oxygen, so the hybridization is the same. If we look at the inductive effect, there is this other oxygen that would seem to influence the electron density of this hydrogen, making it more acidic. So that is one thing to speak of. There is also resonance in both of the conjugate bases. So if we look at, first, let's look at the acetate. This is the conjugate base of the acetic acid. So this has this resonance, which makes this. And this also has resonance, where this negative charge can go down here to form a double bond, and then one of these double bonds to the carbon can then hold the negative charge. So you would get this. So the problem with this resonance structure is the carbon holds the negative charge. Carbon does not like having a negative charge because it's not very electronegative, whereas the oxygen does. So in terms of resonance contributors, this doesn't contribute very much, meaning it's not a particularly stable resonance structure, and it doesn't do very much for the acid strength since this is a rather weak resonance structure. So, putting it together, when we consider partial influence of the inductive effect here because of the presence of this oxygen, and this is a better resonance structure, this contributes more to its resonance, we know then that this is the stronger acid, and the stronger acid is on the right side, so we want to drive the equilibrium away from that to make its products, so it's driving the equilibrium to the left. So the equilibrium lies to the left. Okay, hopefully that makes sense. I have two more examples that I want to work through. Okay, so here, again, no pKa's, so we have to determine the acid and bases initially. So here we have a proton that's being donated to this molecule. So this is a Bronsted-Lowry acid. So that makes this the Bronsted-Lowry base. And therefore this is the conjugate base, and this is the conjugate acid. Now, what we have to compare is the acid strength again here. So all we have electronegativity and size to consider. So oxygen is more electronegative than sulfur, which suggests that this acid would be stronger. But remember, if we have a size difference, that matters more. So sulfur is below oxygen on the periodic table, making this a much larger atom than oxygen. So because of size, this is the most acidic molecule, has a lower pKa than this. And also, just to be complete, there's no inductive effect to speak of, there's no resonance in either of these conjugate bases, and there's no hybridization difference. So because of that, this molecule is the strongest acid, which drives the equilibrium away from it, which is to the left. So equilibrium lies to the left again. Okay, and our last question for the day, our last example here. So again, there's no pKa values that have been given to us, so we have to identify which is functioning as the acid and base. So here we have a proton being donated to this molecule, so this is our Bronsted-Lowry acid. Here is our Bronsted-Lowry base. Therefore, this must be our conjugate base to our Bronsted-Lowry acid, and this must be the conjugate acid. So now the question is determine, is this acid more acidic than this? And this is relatively easy to identify because here we have size difference and electronegativity difference again with the hydrogen and Cl and oxygen and hydrogen here. So because of that, this is definitely the stronger acid because of electronegativity and size. So that drives the equilibrium to the left, away from the stronger acid. So with that, that is all I have for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. And if you have a topic idea, please feel free to leave it in the comment section below, and I will get to it as soon as I can. So I hope you have a great day, and I'll see you all in the next video.